Good morning to everyone. Last video we have discussed about the element equations and then behavior of element equations, actions and then properties. In this video we can going to discuss about the assembly of element equations. So assembly of element equations to obtain global or structural equations. The objective of the assembly all the equations is to be obtained equations for the entire body or a structure that defines approximately the behavior of entire body or structure. So in this, we can derive the equations for an individual elements. Finally, we want to assemble all the element equations put together to get as an global equations of entire structure or a body. These equations will give the inputs from the structural related things, and then the behaviors will be based on the global equations. Once the element equations are established for an generic element, we generate repeatedly the equations of all the elements. Then we add them together to obtain the global equations. We can derive the equation for a single element. That equations will be repeatedly for all other elements to calculate the values. Then finally all the element equations combine together to set as an global equations. For example of equations, already we have discussed general equations. So element stiffness matrix into element displacement equal to element force vector. Finally, we get as an global stiffness matrix into global displacement vector equal to force vector. So this is the assembly equations. For example, assembly of both the element matrix is called as an assembly of element equation. So here the indication of two springs. This spring 1 will be an element 1, the spring 2 will be an element 2. In this each spring they are having a two nodes. For element 1, node 1 and node 2. For element 2, node 2 and node 3. The stiffness value for element 1 for spring 1, K1. The stiffness matrix for element 2 is called as an K2. For node 1, the input value will be an F1 and then behavioral output will be an U1. For node 2, the action input value is F2 and then behavioral U2. Node 3, the action will be an F3 and behavior will be an U3. If we are assembling the equations for particular two springs, the force value will be an F1, F2, F3. So totally they are applying of three forces. And then displacement will be an U1, U2, U3. It will be indicated here. And then behavioral matrix, so stiffness matrix is in K1 minus K1 minus K1, K1 for an element 1, K2 minus K2 minus K2, K2 for an element 2. So for global equation, K1 minus K1 0 minus K1 K1 plus K2 minus K2 0 minus K2 K2. So this is the global stiffness matrix. This is the assembly equation. Next we will move to the boundary conditions. The geometry or essential boundary conditions. Either it will be in geometry conditions or essential boundary conditions are prescriptive value for a nodal deformations. They are also called as an geometry or kinetic boundary conditions. If any geometry conditions or essential boundary conditions, the displacement values will be applied at the nodes based on the degrees of freedom. We are going to constrain the degrees of freedom. It will be in single degrees of freedom or multi degrees of freedom. For beam, we are constraining the displacement about x direction and then structural about y direction also. In natural or non-essential boundary conditions are prescribed value for higher derivative of field variables, then that are used as a nodal deformation. So in natural or non-essential boundary conditions are prescribed for an higher derivative values only, not for an local areas. This is the boundary conditions. Thank you for watching video. We'll see you in next video. Thank you.